Why would it hurt if I were to say throw a brick at you? Because the brick is moving, it has what we call kinetic energy. Kinetic energy is the energy of an object due to its motion. An object with kinetic energy also has the ability to do work or to cause pain. Think of swinging a hammer. The kinetic energy of the hammer allows it to do work on the nail or to cause pain on your thumb. There's actually two types of kinetic energy, though we're only going to deal with one of them. There's rotational kinetic energy and a linear kinetic energy. We're going to focus on the linear version of kinetic energy. Linear version is called translational kinetic energy. Let's go back to our brick. Why would it hurt more than, say, a pebble I were to throw at you? It's because the brick has more mass. Kinetic energy is directly proportional to mass. Is there anything I can do with the pebble to make it hurt as much or even more than the brick? Sure, if I would throw it fast enough. Kinetic energy is proportional to the square of the speed. Note that it's speed, not velocity, because kinetic energy is a scalar quantity. And also that it's proportional to the speed squared. Kinetic energy is equal to 1/2 the object's mass times its speed squared. And just like work, it's measured in joules. Work and kinetic energy having the same unit gives us a hint about their relationship. The net work done on an object is equal to the change in its kinetic energy. This is called the work energy principle. The net work equals the change in the kinetic energy. If the net work is positive, kinetic energy will increase. And if the net work is negative, kinetic energy will decrease. Hey guys, real quick. First person to email me the number of fingers I'm holding up gets 100 on the next quiz. Let's look at an example. Here we have two identical cars, except for car B is going twice as fast as car A. If car A slams on the brakes and is able to stop at some distance D, how much farther will it take car B to stop? So first, let's figure out how much more kinetic energy car B has. It has the same mass, but twice the speed. And since kinetic energy is proportional to the speed squared, twice the speed results in 4 times the kinetic energy. So if car B has 4 times as much kinetic energy, how much work is going to be required to stop it? So work is equal to the change in kinetic energy. We're going from some value, which is 4 times as much as A, to 0. We can see that the amount of work is proportional to kinetic energy. So if car B has 4 times the kinetic energy, it's going to require 4 times as much work to be done to bring it to a stop. What's the relationship between work and the distance? We're assuming the same frictional force is acting on both cars, so we can see that the work is directly proportional to the distance. So car B will take 4 times as far to come to a stop. Let's look at a couple questions. Rank in order from greatest to least the kinetic energies of the sliding pucks. So you have 4 different pucks, different masses, different speeds. So to find the kinetic energies, we can use 1/2 mv squared. All right. And if we do that for each of the pucks, we'll get 2, 4.5, 2, and 4. Notice that A and C have the same kinetic energy, even though C is going to the left, because kinetic energy relates to speed, not velocity. So direction doesn't matter. So our ranking then, we put them in order, gives us B is greater than D, which is greater than A, which is equal to C. So notice that with D and B, D has a greater mass, B has the greater speed, but since kinetic energy depends more on speed than it does mass, B will have the greater kinetic energy. Here's a second question. A block with an initial kinetic energy of 4 joules comes to rest after sliding 1 meter. How far would the block slide if it had 8 joules of initial kinetic energy? So in this situation, we have twice the kinetic energy, right? Because you go 4 to 8, so it's twice the kinetic energy. So that means we'd have to do twice as much work to stop the block, which means it would slide twice as far. Let's look at a couple example problems. How much kinetic energy does an 80 kilogram man have while running at 1.5 meters per second? So kinetic energy is 1/2 mv squared. So we'll do 1/2 the mass of 80 kilograms times the speed, the 1.5 meters per second squared. Not just the 1.5 is squared. So 1.5 squared is like 2.25 times half of 80, which is 40, gives us a kinetic energy of 90 joules. Number 2, a bird flies at a speed of 2.3 meters per second. If it has 14 joules of kinetic energy, what is its mass? So kinetic energy 1/2 mv squared, but we're going to have to rearrange this for mass. So if you multiply both sides by 2, and then we divide by the speed squared, our mass will be 2 times the kinetic energy divided by the speed squared. So 2 times 14 divided by 2.3 squared gives us a mass of 5.3 kilograms, which is a fairly large bird. It's like a 13-pound. It's a turkey flying around. Thanksgiving turkey. All right. 3. Child plus 12 joules of work pushing his 3-kilogram toy truck. With what velocity does the toy move after the child is done pushing? It's kinetic energy 1/2 mv squared. Now this time we have to rearrange the equation for speed. So we're going to multiply both sides by 2, divide by m, and then take the square root. So the speed is 2 times the kinetic energy divided by the mass, taking the square root of that whole thing. So you have 2 times 12 divided by 3. 2 times 12 is 24. 24 divided by 3 is 8. The square root of 8 is 2.8 meters per second.